Oh, okay. Thank you. Okay, thank you. Yeah. Good afternoon. Today I'll be presenting some of my ongoing investigations into positron acceleration using plasma-based accelerators, which I guess is the theme of this workshop. And I'll show you basically, I'll go through the motivation, the current challenges, and the current possibilities and opportunities to address these challenges. And this talk, for those of you who attended the Newton Bhabha High Field Science Workshop in Trivandrum, this is sort of a continuation of that talk. And I'll be showing the efforts that we have put together going forward on this topic. So let's first look at the motivation for investigating positron acceleration using plasma-based techniques in particle acceleration. And I think the one major motivation that is easy to identify is building electron-positron colliders for investigating particles such as Higgs Boson, and further investigating particles such as Higgs Boson, and actually even addressing the SUSY particles, which are even heavier, which are supposed to be even heavier. So if you look at this graph here on the slide shows an evolution of the electron-positron collider based on their center of mass energy. And the years over which these have been explored. So as you can see, the highest, the 1 TeV sort of scale for a linear collider is required to address the challenges that I just mentioned. So the goal for a positron for the positron acceleration effort is to be able to technologies, the more underlying technologies that will take the energies of the positron beam possibly towards a TeV. And just to give you a state of the art, currently there are several interesting results on positron acceleration, but none of them are entirely convincing. So this is the main sort of the push towards it. And to give you more specifics, there is a plasma-based collider design which uses the beam-driven plasma wave method. And as you can see on this slide, this design is based on what is called as staging multiple cells of plasma acceleration. And it has so the right-hand side of this simplistic conceptual design is still under a big R&D, and not to mention that even the staging setup for electron acceleration is not yet fully explored and fully parameterized and understood. So there is obviously a big effort going on in staging setup for electron acceleration, and also just investigating positron acceleration. So a similar design for a collider, of a plasma-based collider, is also out there for laser-driven structures. And again, the goal is, this is, for example, a 2 TeV center of mass energy collision at the collision point design. And I assume that even a 500 GeV collider would be a pretty good option for Higgs boson and SUSY. So in this design, again, the right-hand side, which is the TeV positron side of the collider, is vastly unexplored. There is a lot of effort on the theory side to investigate the positron acceleration angle better. But again, as I mentioned earlier, with the beam-driven case, the setup for the electron acceleration is not yet fully explored. So this is basically the motivation for further exploring positron acceleration in both beam-driven and in laser-driven plasma accelerators. Apart from this main motivation, there can also be several other applications of positron beams that are driven by compact accelerators in general. Especially for medical diagnostics, for techniques such as the positron emission tomography and similar things. But we are not entirely sure if the sort of energies required for a positron beam in that kind of setup are very, very challenging for plasma. So let's move on to the main challenges. Apart from the sort of the technological challenges of staging, the positron acceleration in plasma-based accelerators suffers some very inherent challenges in terms of both transporting and accelerating the positron beam. So the first sort of question or challenge for positron acceleration is, unlike the self-injection method which is used for electron accelerators to basically inject the electron beam in the right phase space volume of the plasma wave, positron beams up to now would mostly have to be accelerated using external injection, which sort of places a restriction on where you can inject those electrons relative to the beam driver, and the whole problem of synchronizing the right phase of the plasma wave to the accelerating beam. In addition to that, the phase space volume of the plasma wave, which is available for transporting positrons, poses a challenge. So let me just give you a very simplistic picture of the second challenge. So if you think about a simple linear plasma wave, which in this picture is being driven by a laser pulse, and this is a 2D PIC simulation, you can see that there is a density buildup, electron density buildup in the blue regions, in the blue-purple regions, and there is an electron density evacuation in the sort of green, yellow, orange regions. And as you can imagine, in the regions where electron density is evacuated, the net charge density there is positive. And you would want to accelerate, so the electric field profile would be, based on Poisson's equation, would be maximum a positive field in between the two regions, in between the negative and the positive region. So you would want to place the positron beam somewhere in between these two. However, if you look at it carefully and look at the theory of linear waves carefully, only half of that phase space volume is actually available for transporting the positron beam, because the other half is defocusing for the positron beam. So already with the linear waves, you can see that the whole problem of putting the electron beam in the right phase space volume is a challenge. Moving on, the laser pulses, if they have to be self-guided in the plasma, if there is no external guiding, if there is no wave guide, or there is no density, profile-based method for guiding available, then lasers have to be self-guided in the plasma. And typically, when you self-guide the laser pulse in the plasma, the laser eventually enters into the nonlinear regime of the plasma wave, because the idea is that the laser has to drive its own refractive index gradient to guide itself. So if you look at these three curves that I'm showing you on the bottom here, in the linear regime, if you think about the half space that I just showed you earlier, that seems to be this volume. On the top is the accelerating field, and in the bottom is the focusing field. So this is the region where you can basically choose to put your externally injected positron beam. If you move to a mildly nonlinear plasma wave, which is with A0 of 1.8, you can see that this volume has reduced to a slightly smaller value. So this synchronization challenge becomes even harder. And then if you eventually enter into the blowout regime, or the most nonlinear regime, you can see that the only region where you can basically inject those positrons is right in the back of the bubble. So what all this boils down to is that as soon as the externally injected beam outruns the plasma wave phase velocity, you can no more have it in the optimum phase, and and the beam might eventually actually also lose energy. So this basically shows you the sort of challenge. So in beam-driven waves, there is a similar problem, but fortunately for beam-driven waves, the phase velocity is, if the beam-driven waves are being driven by a beam which is of a very, very high value of gamma, or the Lorentz factor, then the accelerating beam wouldn't eventually outrun the phase of the plasma wave, but still the region available for accelerating positrons is very, very tiny in the blowout regime. So these are the challenges, and then let's look at what are the possible solutions that are currently available or currently proposed. I was able to only narrow down to these three main possible areas by which you can address the positron acceleration problem with some conviction. I mean, obviously there is always an argument saying that you can load those positrons in the blowout regime with some precision, and you can achieve acceleration of positrons, but that is not a lasting solution, because we have to think about the stages of positron acceleration which are in the later part of the acceleration chain in a collider, and in that case the drive beam and the accelerating beams have become much more dense because they are undergoing adiabatic damping, and it's not easy to load that type of a beam exactly in the blowout regime. So the proposed solutions are, one of them is a hollow plasma channel. And as you can imagine, in a hollow plasma channel, the positron beam never interacts with the ions. Or putting it in another way, in a hollow plasma channel, the focusing phase is with the conventional understanding non-existent. So the positron beam never suffers the defocusing force, whereas it can just purely accelerate. So all of the focusing force on the positron beam would be from what it was focused to before it enters the plasma. So that is the conventional understanding. However, in some of my work, I've shown that there is a possibility to go into what is called as the crunch-in regime, wherein you can drive the hollow plasma channel into a nonlinear mode where you can sustain also focusing forces in addition to the accelerating forces. So I'll be talking about that today. The other possible solution is the hollowed out laser mode, the LG mode solution, and this has been proposed in this paper that I cite here in 2014. The basic idea here is that the laser pulse that is driving the plasma wave is essentially hollow in the center, and by using the modified quantum motive force setup, you can drive excess electrons back onto the axis of the plasma wave, and by using these excess electrons as the focusing as imparting the focusing force on the positron beam, then you can accelerate and transport the positron beam and achieve positron acceleration. The third possibility, which I'm exploring currently, which I don't think has been explored much especially for laser-driven possibility, is using a leptonic beam, which is basically a reduced space charge beam wherein there is equal amounts of electrons and positrons in the beam. So the beam suffers. So when the beam propagates in the plasma, even though the positron beam is suffering defocusing, the electron beam, which is co-propagating with it, might be able to keep it in focus for much longer than what is possible with just the positron beam. And there is some possibility of doing some experiments at Rutherford Appleton Lab using the Gemini laser. I'll show you shortly. So let's more closely look at the hollow channel approach to solving the positron acceleration challenge. For example, this is a result from the FACET facility at SLAC, where they achieve a multi-regime. They have not used a hollow plasma channel, but they are aware that to avoid the problem of defocusing of the positron beam, there is a proposition of using hollow plasma channel, which produces zero focusing forces. So the positron beam never undergoes any defocusing at all when it's in this hollow plasma channel regime, right? And this claim is based on a well-known work where Katsoulias and Chiu showed that have shown analytically that the focusing forces inside a hollow channel are essentially zero for a relativistic particle driving the hollow channel. And further theory explains that the acceleration field comes from the electromagnetic fringe fields of the wake that extend back to the center of the channel. So we are talking about a cylindrical hollow channel here, and the assumption is that there is vacuum in the center of the channel, and there is homogeneous plasma outside the channel. So when the electron beam or a positron beam or a laser pulse goes through this hollow channel, it drives the walls of the channel, and the electrostatic fields are excited in the walls of the channel, but electromagnetic fringe fields basically leak back extend to the center of the channel, and that enables focusing and acceleration of particles down the axis. So obviously these wake fields arise from the surface currents, and there is more work on understanding these hollow plasma channel forces, focusing forces and accelerating forces in a near hollow plasma channel, because perfect hollow plasma channel might not be technologically possible. And again, what is shown here is that the electromagnetic wave, which is driven by the surface currents, is the one that that drives the positron acceleration. So let's look at what's going on in such a channel. I'm showing you here some 2D PIC simulations of the laser-driven hollow channel mode, where the laser is 4. Its waist size for a Gaussian laser pulse is 2.5 times the skin depth, and the homogeneous plasma frequency, which is outside the channel, its ratio to the laser frequency is about 30 times. And the channel width here is 3 skin depths. So that laser basically propagates down this channel. It excites electron-ion charge separation in the walls of the channel, and that leads to these fields, which are 10 to the minus 3 of the wave breaking. So this interaction will have to continue for much longer than in the blowout regime, for example. And similar things can be shown for electron beam. This is a cylindrical geometry simulation. Electron beam drives these surface currents on the walls of the channel, and you can see that there is corresponding accelerating and decelerating fields, and there is nearly zero focusing field on axis in this case. Again, the fields are of the order of 10 to the minus 3 wave breaking. And similarly for the positron beam, you can again see there is accelerating field, which is the red region. There is zero focusing forces, so the positron beam never experiences any defocusing at all. However, all of this is based on the theory of linearly driven hollow channels. In linearly driven hollow channels, there is no collapse of electrons from the surface walls back to the axis of the channel. And if you drive the channel non-linearly, there is a possibility to make the electrons collapse back to the channel from the walls of the channel. And thus, in that case, the fields are not purely electrostatic. And this has been, and in some works this has been recognized that for the linear analysis to be valid, the surface plasma density perturbations should be much smaller compared to the channel radius. So what we are exploring is what is called as a non-linearly driven hollow channel regime. And in this regime, just comparing in a very basic way, if the red curve corresponds to the surface perturbations in the linear regime, in the nonlinear regime, the electron oscillations would have trajectories back down to the axis of the channel, which is actually shown here. So here, what I'm showing you is a hollow channel with a radius of 0.5 C or omega p, and there is homogeneous plasma density outside. And you can see that these electrons, which are originating in the surface of the walls of the channel, basically collapse back to the axis. So that's why I call this a crunch regime. And most of the electric field for acceleration, which is shown in blue here, and the focusing field, which is shown in red, are based on these the electrostatic force of this electron bunch that collapsed back to the axis. So because this is a nonlinear regime, we can see that the magnitude of the accelerating field depends upon the beam parameters. So I'm comparing three different beam parameters here. The beam radius of sigma r 0.3 and NB of 2.5 has fields which are much higher than beam which has sigma r of 0.3 and beam density of only 1.3, the plasma density. And then eventually you can see that if we increase the beam charge even further, then the possible fields can be as high as 0.4 the wave breaking, whereas earlier in the linear regime, we only had 10 to the minus 3 of the wave breaking. This is some background theory, which I'll leave for later. Similarly, you can drive these crunching regime modes using an electron beam driver. So the electron beam is driving an electrostatic mode, which is again causing these walls electrons to crunch back to the, and again the fields here are of the order of 0.4 the wave breaking, and there is a region of focusing force available for positrons to be loaded as well. And similarly, in laser-driven hollow channel plasma, you can also show that there is a possibility to drive behind the laser pulse drive in electrostatic mode, where the electrons originate from the walls of the channel. So let's quickly move on to the other idea of using a leptonic beam. In the leptonic beam, the main motivation is can having a nearly neutral mix of electrons and positron particles in the beam allow sustained acceleration of positron beam. So the essential idea, as I outlined earlier, is that if the electron beams are co-propagating with the positron beam, then even if the positron beam suffers a defocusing within the plasma, at the same time electron beams are undergoing a focusing, then there can be an electrostatic imbalance between the electrons and positrons, which will cause the positron beam to be defocused less than what it would be in the case where it was just positron beam. And this is motivated also by possibility of doing an experiment at using the Gemini laser, which has 2 laser pulses. So you use the first laser pulse to drive the first stage of plasma acceleration, where you have just electrons being accelerated, and then you use a positron target in between the 2 cells, and this positron source will basically use the pair production process of when the electron beam goes through this high Z material and generate a corresponding positron beam as well, which will then be injected into a second gas cell stage, which is driven by the second laser pulse of the Gemini setup. And the reason this is being proposed is because earlier using the Gemini laser, it has been analyzed that you can actually generate neutral and high density electron positron pair plasma, where the electron positron beam basically has the same sort of energy profile as the original electron beam. So what are we currently doing? We are trying to model this leptonic beam behavior interacting with the plasma wave better, and we are able to show that we can gain about a GeV energy for an initially injected positron beam, and we are also able to show that in some cases we are able to double the energy of the initially injected positron. And this is a current proposal for doing this experiment at Gemini, which we submitted last year in November, and we are planning to resubmit it for this cycle of the upcoming CLF call for proposals. So summarizing the main points of this work, positron acceleration using plasma wave is an active area of research. There is research going on both in beam-driven and laser-driven. Understanding the theory of both the cases. For hollow channel, the current ongoing work is on generating the hollow channel in the plasma, which is not easy, especially if you want to use the hollow channel mode over a long distance. It's easy to generate a homogeneous plasma over several centimeters, several tens of centimeters, but it's hard to generate a corresponding hollow channel. The other work which is going on hollowed out laser modes is on generating these hollowed out laser modes at high intensities. And there are several very interesting recent publications on using Raman amplification of this seed LG mode. Regarding the leptonic beam work, there is currently work going on setting first of all setting up a staging setup which has which is one of the steps for a collider as well, which is using an electron beam from a previous stage and using that same using the electron beam which is accelerated by the first stage to undergo further acceleration in the second stage. So that's something which we are getting ready to do sometime later this year. And currently there is lots of simulation work on looking at the acceleration of leptonic beam for positron acceleration. And just to summarize, my last point is that there are several existing facilities like Rutherford's Gemini, and there are also several plant facilities like Facet 2 and Flash Forward, which will be able to address these challenges of positron acceleration in a much more concrete way by using having a synergy of both simulations and experiments going together. So thanks a lot. Any questions, please?
You mentioned in the beginning 500 GeV or 1 TeV electron-positron linear collider by using laser plasma acceleration method. When will that, can you give me a timeline, approximate timeline, when that is feasible, when that will become feasible?
I think on a time scale, I think we at least there has to be more R&D for between 5 to 10 years. But from my understanding, it also appears that the amount of funding available currently for taking this forward also decides the time frame. So the answer depends on how much opportunities are available currently to explore these areas. But yeah, definitely between 5 to 10 years, not before that.